So we're going to do a brief introduction to matrices and talk a little bit about how they relate to systems of equations. So let's get the idea of a matrix. A matrix is an array of numbers that looks something like this. Usually index them by row and column. So this would be A11, A12, A13 out to A1n. And then A21, A22, A23 out to A2n. And then, let's see, I think I did A31, A32, A33 out to A3n. And then we go down to AM1, let's back that up a little, make this look a little neater at least. Down to AM2, down to AM3, and all of this is going to lead to AMN, right? So we would say that this is an M by N matrix, M by N matrix. And another way we can write this is we can say A is an element of the M by n matrices. So that capital M means the set of all matrices. So how does this relate to when we're talking about systems of equations? Okay, so let's do a 3 by 3 system of equations. I have x1 minus 4x2 plus 3x3 is equal to 5. Negative x1 plus 3x2 minus x3 is equal to negative 3. 2x1 minus 4x3 is equal to 6. Now, from the row operations business that we did last time around, you'll note that there's a lot of extra notation in this that you really don't need. So what you can do is you can turn this into an augmented matrix, and you just kind of work your way across. 1, negative 4, 3, 5. Negative 1, 3, negative 1, negative 3, 2, 0, negative 4, 6. So this augmented matrix, so this is a matrix, this is an augmentation, can be used to symbolize that system of equations in such a way that you can do things like elementary row operations on it and not actually have to keep carrying along all the variables in the notation. So recall the elementary row ops are the same as they were when we were working these as equations. You can interchange two rows, or you can multiply a row by a non-zero constant. Or 3, you can add a multiple of one row to another. Those 3 were the 3 things that we could do to a system of equations and not change its solution. Likewise, these are 3 things that you can do to an augmented matrix and not change the solution of the system that it represents. So let's work an example with this. So let's take the augmented matrix that we derived from our system. 1, negative 4, 3, 5. Negative 1, 3, negative 1, negative 3. 2, 0, negative 4, 6. Okay, so our goal is again to create a row echelon system of equations. So if I simply add row 1 to row 2 and replace row 2 with that, all right, so row 1 is going to stay the same, 1, negative 4, 3, 5. And then we add to row 2, this becomes 0, negative 1, 2, 2, and then 2, 0, negative 4, 6. Okay, So you can see that this kind of speeds up the process a little bit because I no longer need to carry all that variable weight with me. All right, so we're going to multiply the second row by -1, so we make this guy a 1, and then replace the second row with that. So first row is staying as it is. The second row is being multiplied through by -1, and it is where we need it to be in order to have row echelon form. All right, so we need to get rid of this 2 here in the third row. Okay, and we do that by multiplying the top row by -2 and adding it to row 3 and replacing row 3 with that row. So the first row is 1, -4, 3, 5. Second row is still 0, 1, -2, -2. And now we're going to multiply this by -2 and add it to the third row. So this is going to be 0. Let's see. -2 times 4 is 8, plus 0 is 8. Okay. -6 plus -4 is -10. And -10 plus 6 is -4. All right, so now my problem is this 8. And I get rid of that by multiplying row 2 by a -8 and adding that to row 3 and replacing row 3. Okay, so the top 2 rows are not going to change. And the bottom row, well, let's see, 0, -8, 0. That's going to be -16, or +16 minus 10 makes that 6. +16 minus 4 makes that 12. Okay, so, and to get it into row echelon form, I take 1/6 times row 3 and replace that with row 3. So this is going to give me 1, -4, 3, 5, 0, 1, -2, -2, 0, 0, 1, 2. Now, why is this useful? All right. This is useful because this matrix, when I convert it back into a system of equations, is going to be, so what I want to use, is going to be in row echelon form, and then I can do back substitution. So let's kind of take a look at how that works. Hold on one second, I'm going to clear some space. Okay, so I've cleared stuff out and left this little matrix down here in the corner. So I'm going to change that back into a system of equations. So that's going to be x1 minus 4x2 plus 3x3 is 5. X2 minus 2x3 is -2. And x3 is equal to 2. Okay, so back substitution, x3 is 2, which means x2 minus 2 times 2 is equal to -2. So let's see, this is going to be -4, so that's going to make x2 2. And then x1 minus 4 times 2 plus 3 times 2 is equal to 5. So let's see, this is going to be 6. 6 minus 8 is -2. Add 2 to both sides. X1 is going to be 7. So this means that 7, 2, 2 is the solution to that system of equations. And because this was determined by row operations, it's the solution also to our original system of equations. Okay, so we're starting to speed up this system of equations process, but it's still a little bit slow. Okay, so let's do some defining here, and then we'll get into a little bit more about technique. Okay, so we have now a row echelon form for matrices, right? So if A is an m by n matrix, such that each of the components of A is Aij. Then Aij has to equal 0 when the row is bigger than the column, and Aij has to equal 1 when I is equal to j. So this will give me a row echelon matrix. Okay, so what I'm going to do here is be a little bit clever. All right, now let's just do this. I can get a reduced row echelon matrix, also known as RREF, right? So this is also an AM by N matrix such that A is Aij. The two former characteristics, Aij has to be 0 when I is greater than j. Aij has to equal 1 when I equals j. And Aij also has to equal 0 when I is less than j. And, okay, so there's an important and here, and j is less than or equal to m. So within the main part, the non-augmented part of the matrix, basically we just have ones down the diagonal and zeros everywhere else, okay? Now, when you add the augment, there's something going on here, and we'll look at what that is, but that's kind of what's going on there. All right, so let's see why this might be important. Oh, important note. To get this form of the matrix in MATLAB, you use RREF on matrix A. So reduced row echelon form on matrix A, and it will do this. Okay, so let's take a look at that. Okay, so we're going to work one by hand, and then we'll probably never do this by hand again, but that's okay. So where we left off getting it to row echelon form was we had this augmented matrix, 1, -4, 3, 5, 0, 1, -2, -2, 0, 0, 1, 2. And then we back substitute it. But we can go a little bit further. We can take row 1 and subtract 3 times row 3 and substitute that back into row 1. That's going to clear out that 3 and make it a 0. Okay, so if I multiply the third row by 3 and add it to the first row, the 1's still going to be a 1, -4 is going to be a 4. Okay, -3, that's going to be a 0. -3 times 2 is -6, so that becomes -1. 0, 1, -2, -2, 0, 0, 1, 2. Okay, so let's do another row here. So now the one that's kind of needs to go away is this -2. So we're going to multiply, or we're going to take row 2, and we're going to subtract 2 times row 3 and replace row 2. So leaving the top row alone, 1, -4, 0, -1. This is going to become 0, 1, 0. Let's see, -2 times 2 is -4 plus -2. Let's see, is up. That's my issue. This is a -2, so this has to be adding. 2 plus -2 is 0. There we go. 2 times 2 is 4, minus 2 gives me 2. That's better. And 0, 0, 1, 2. Awesome. All right, so we've got to now get rid of this -4. So we're going to take row 1. And now we're going to multiply 4 times row 2. And we're going to add that back to row 1 and make that the new row 1. All right, so like if I multiply this by 4 and add it to the row above, this stays as 1. That's going to go to 0. That's staying 0. 2 times 4 is 8. Minus 1 is 7. That's nice. And these two stay the same. And lo and behold, that's my solution. Why is that the solution? Because if I read this augmented matrix, it says x1 is 7. It says that x2 is 2. And it says that x3 is 2. That's my solution set. So when I do something in reduced row echelon form, the last augmented column will actually possess, if it exists, the solution to my my system of equations. So what we just did here is something called Gauss-Jordan elimination. Okay. This is one of the very few critical algorithms that is used. So you first use row operations to take your augmented matrix to row echelon form, and then do more row operations to get it to reduce row echelon form. And when I do this, if I have a solution to my systems, it will pop up in that last column. Now, what is really critical here is that MATLAB has this function built in. So let's try one more example. Okay, so let's take a look here. Let's say I have x1 minus 2x2 plus 3x3 is 9. Negative x1 plus 3x2 is equal to negative 4. And 2x1 minus 5x2 plus 5x3 is equal to 17. So the augmented matrix would be 1, negative 2, 3, 9, negative 1, 3, 0, negative 4, 2, negative 5, 5, 17. Okay, so this is when I want to hop into MATLAB. Okay, so hold on. Okay, so we're going to note that the mat in MATLAB actually stands for matrix. Okay, so this is a matrix laboratory. So we're actually in MATLAB's like natural space. So we don't have to do like dots and times's. We can just use the operators here. So I'm going to make my augmented matrix. Okay, so I put a bracket there and I put it in the first row. 1, negative 2, 3, 9. MATLAB doesn't care this is augmented, so I don't put the little bar in there. Semicolon gets me to the next row. Negative 1, 3, 0, negative 4. Semicolon brings it to the next row. 2, negative 5, 5, 17. Now, separating, you can either use commas to separate or you can use spaces. It is my habit to use spaces to separate between elements, but you can use commas. It just feels to me like a lot more clunky. Okay, and if I do that, there's my matrix. And I say to matrix MATLAB RREF matrix A, and boom, it returns the reduced row echelon matrix in one step. Okay, so if you look at this right here, the 1, negative 1, 2 is the solution to my system of equations. So I've gone from having the system to the solution in one computational step using MATLAB. Now, honestly, you can also do this with your TI-84 calculator, but it's a little bit more clunky because the TI-84 calculator is not as easily robust as MATLAB. All right, so give me a moment here and I will find that. Okay, so let's say you're in an environment where you have the calculator but you don't have MATLAB. Let's see how this works. I'm going to go second matrix and I'm going to edit matrix A. Now my augmented matrix here is 3 rows and 4 columns. And I'm going to put in the augmented matrix. 1, negative 2, 3, 9. Negative 1, 3, 0, negative 4, 2, negative 5, 5, 17. And then I'm going to go back to the main screen. I'm going back to my matrix menu, and I'm going to go to math. And the function that I want is all the way down here at the bottom. It says RREF. And I'm going to do that on matrix A. And lo and behold, your TIA calculator can actually do Gauss-Jordan elimination. And it gives you the answer just as before, 1, -1, 2. So there you have it. There's your intro to matrices. We'll look some more depth of like special cases of this next time around. But there you go.